All right, well, good morning, everyone. Welcome back to another exciting day of mathematics. How's everybody doing? Good? How was home plate? Yeah, let's go. So warm up number 52 is on the screen. And once again, we've been working on these already for about a week. So hopefully you got these. Warm up number 52 reads, number one, computes the sum difference in product of 7 plus 5i and 15 minus 3i. And that was last night's home plate, BTW. Number two, it says solve x squared minus 4x minus 12 equals y. You know different methods of doing that, so hopefully that should be a piece of cake. Number three, it says graph f of x equals x squared without a table. We know how to do that. And then it says write the rule and graph, use the vertex for the transformation. And it gives you the general form g of x equals AF of 1 over BX minus H plus K. And for the parameters, they give us A equals 1, B equals 1, H equals -4, and K equals 5. Last but not least, number 4 says solve the system using substitution. And they give us a system y equals 2x plus 3 and y equals -x minus 6. I'll give you some time for that. Copy and go. All right. Let's see what we got for number one. Let's see what you get for number one. For the sum. Raymond. 22 plus 2i. Hands, have you got that? That is correct. Difference. Pass someone. Brooke, what'd you get for the difference?
I got
-8 plus 8i. Hands, have you got that? That is correct. Don't forget to distribute that negative. Product, pass someone. Philip.
120 plus 54i.
120 plus 54i. Hands, have you got that? Looks about right. Yes, that is correct. Make sure if you didn't get that, at the end, you should have substituted -1 for I squared. That was a home plate. All right. Number 2, Philip, pass it to someone.
Newer.
Noor, what method did you use to solve this quadratic equation? Completing the square. Okay. Did anybody use any other method? Yes? Factor? Okay. Let's try factor just to go a little bit faster. Is that okay? All right, so 0. So that means factors of -12 that add up to -4. What two numbers multiply give me -12 that when you add them give us -4? -6 and 2. So my two factors are x minus 6, x plus 2. All that equal to 0. Set each one equal to 0. X minus 6 equal to 0. X plus 2 equal to 0. Then we solve. Plus 6, x equals 6. Minus 2, x equals -2. And by completing the square, you should have gotten the same thing. Yes? Hands, have you got that? Okay, pretty good. Yes. Let's go to number 3. Before I continue with that one, share with your neighbor. This is a general rule. These are the parameters. How would you rewrite the general rule for the transformation using those parameters? Have it over to your neighbor, please.
Oh, no, it's not.
All right. So first, let me graph the original parabola. The original should go somewhere right here. So far, so good, yes? Yes, Mr. Q. All right, good. And then our general rule, if I substitute here 1, and then the -4 there and the 5 there, what would be our general rule? Carlos. G of X equals, let's go. Hands if you got that. All right. Now we're going to move this vertex, the 0, 0 vertex. We're going to move it to a new vertex. Tell your neighbor the new vertex for that transformation. What's our new vertex? All right, let's see. How about Juliana? -4 and 5. Hands if you got that. That is correct. -4 is over here. 5 is up here. So that new vertex is somewhere up here. And this will be my G of X. All right. All right. Last but not least, show of hands if you haven't finished number 4. Okay. So the majority already did. I'll give you one more minute. Turn to your neighbor, let them know how to start substitution method for that one, please. All right. So now that we know the method and you know what to do, what you get at the end, Andrew. -3, -3. Hands if you got that. That is correct. So you never what that means. What does that mean? -3, -3. What does that mean? It's a solution, but what does it mean? Let's see. I want to pick someone to elaborate for us. What does that mean? Good conversations. Let's see. Audrina, what does that mean? You ever hear that?
No.
A little bit louder, please. The intercepts of the two graphs, that is correct. If we were to graph these two lines, that's where they're going to intercept, all right? Copy the agenda for today. Agenda, warm-up number 52, complex numbers, and home plate pages 135, 136 only. Copy that. All right, your Nearpod code is on the screen, XF6KU. XF6KU. In there, you're going to find the play sheet or the pages 135, 136, which is your home plate for tonight. All right, and not just FYI, BTW, you guys heard, I think, yesterday in the afternoon, Mr. Apodaca, right? So those that didn't hear, he was a little bit, sounded a little bit upset. Yeah, a little bit irritated in regards to people with electronic devices and such. And they told us to pick up anything that we saw, like pods, cell phones, or anything that is out and about. I don't know, you know. I think just to kind of like be supportive of our admin team. So yeah, some of you need to like really get to class pretty quick because some of you are taking a little bit too long with your messaging and social media, whatever it is you guys do in between classes. However, I did email them, let them know that in my class, we do need them to turn in stuff because your Chromebooks or the Chromebooks that they got us, they're not touch or writing or whatever, and they're limited. So they gave us a green light. So make sure at the end of the session, make sure you put that away. Yes. All right. So with that said, your home plate from last night, take a picture, turn that in on Canvas, please. Nice.
I still have my Chromebook in my last class.
You can borrow one. It's right there.
I don't know.
Okay, take a pass. All right. And after that, get a Cornell note ready. You don't need a Frere model. There's the objective on the screen. I'll give you some time for that. Hurry up, please. All right, so if you're joining us on YouTube, the code that you see on the top left, that's for a live presentation that we're going to be doing today. That's not going to work for you. You needed to copy the code earlier for the Nearpop presentation. However, in there, guys, remember that you are going to see the 2 pages for home play in PDF viewer. So make sure if you need to get there, go there. Okay. All right. So our objective for today, I can define and compute complex numbers, right? Your objective at the bottom left of your Cornell notes. So you don't need a Freire model today. Today, we're going to go straight through this. And yeah, today's going to be a day to just see a couple of things because we're going to move on with some of the electronic components. Yes? Yes, Mr. Q. All right, so our objective for today, I can define and compute complex numbers. I can define and compute complex numbers. So what is the main concept so far that we're still on? Complex numbers, and we're defining and computing, okay? So before we move on, turn to your neighbor, let them know a quick definition in your own words of complex numbers without looking at your notes. What would be a definition of complex? All right. Brooke is a lot like, don't call on me, Mr. Q. All right, I won't. Lock your toolbar and fill out the Freire model with a text tool. Give me a definition in your own words. One example, one unexample, one hashtag without looking at your notes since you talked it over with your neighbors. Okay, good. I'll give you some time for that. Ready, go. All right, I think we got it. Yes. All right. So you should have gotten something like that. Take your screen. You're like, oh, yes, almost exactly to the T. Yeah. Yeah, but it's amidst because I see it live what you're doing. Yeah. All right. So quick recap. Yesterday, we started with these. Yes. Naming the components of a complex. Gave you guys some of those. And then from there, we moved on to some difference in product of binomials. Yes. Then we did some fun ones like this one. Yeah. And then from there, we moved on to complex numbers and also with some difference in product. Yes. All right. And then I think we stopped. Oh, yeah. We got to the electronic circuits. I introduced a basic one. Yes. Then from there, we moved on to show you different other components. And we said that we're going to focus on 3 components. Is that correct? Yeah. All right. So without looking at your notes, tell your neighbor the 3 components and what is the symbol that we use for those components. Yeah, it's not. All right, good discussion. So with that said, lock your toolbar now. And I want you to write in the name and then draw the symbol. Write in the name, draw the symbol for all 3 of them. I'll give you some time for that. Copy and go. All right, let's see if we got it. The first one we introduced was a resistor. Yes. And we said that one was found, or the basic one that I told you was in a light bulb. Remember when I told you to change the light bulb, the little filament, and they looked like this, a zigzag? Yes. So far, so good. Yeah. The second one I introduced was an inductor. Somebody wrote earlier instructor. No, that's me. Yeah. And an inductor, remember that I showed you with the coil, like how to coil the wire around. You guys can do this experiment by yourself at home with a nail, get a wire it up like that, and then get a battery, like a AA battery, and it becomes a magnet, stuff like that. Yeah. So, and that one looks like this, a coil. Yes. And the third one was a capacitor. And what does a capacitor do? It stops the current from returning back to its source. That's why the symbol looks like that. We good? Yeah? All right. So look up. Then from there, we came to this one. Is that correct? All right. So watch. If I was to label this one more time, check this out. Let me start off with red. I would label this what? What is the name? So I'm just going to label it with a letter R. How about this one? The letter I, that means this one is what? C. Does everybody see what we're doing? Yeah? Yeah. So resistor, inductor, capacitor, but I'm only using the letter so it can go a little bit faster. Yes? All right. So now that we did a quick review on your screen, check this out. Lock your toolbar, and I want you to label that one using initials. Let's see how well you do. Some time for that. Ready, go. Look up. C for capacitor, capacitor, resistor, resistor, inductor. Hands if you got something like that. Yeah, we got this, yes? Let's do another one. Lock your toolbar for that one. See how you do with that one by yourself. Hurry up, hurry up. Label it. All right. Oh my goodness. All right. I get it. Oh my goodness. So yeah, it looks like, all right. Yes, resistor, capacitor, resistor, inductor. Okay, I get your point. My goodness. Let's move on. One more. Copy this one. I'm sorry. Label that one. See how you do. Shouldn't take you long. All right, I think we got it. See some smiley faces. Man, some of you like are writing with your feet or something. What's going on? Look, oh my goodness. What is this?
This must be a cursive I.
Oh, a cursive I. All right. All right, so it looks like we got it, yes? All right, so let's set that aside for right now. And let me go to my presentation really quick. All right, so we got these. So today I'm going to talk about electric circuits a little bit more. So writing your utensils down, look up to the screen. And we're going to talk about current. Now, yesterday I introduced a basic one and it required a battery, yes. And then it had also some wires and it has a switch and a light bulb. And we said that circuits can be found here in the classroom like this light strand with that light strand is on the left switch over there. And bless you. And the other three that are off are on the other switch. So that's a separate circuit. So every circuit has a power source, whether it's a battery or whether it's from the electricity coming from the walls. Now, there's two types of electricity. Look up to the screen. There's AC, known as alternating current, and there's DC, which is direct current. AC is the current that you find on the walls. Because I don't know if you notice, when you plug in your charger, you can either plug it in like this or like this, either way, because it's alternating. You can alternate the way you plug it in at times. However, that's the most dangerous electricity because it starts at 120 volts. How many volts? 120. Now, let's think back. Now, I don't know if you've done this before. Let's see, Philip, have you done this before? That you've gotten those 9-volt batteries, those rectangular ones?
Yeah.
And then put it to your tongue. Have you guys tried that? Yeah, I haven't tried it either. Yeah, no, I have. And you get shocked. You know, I was going to give you like, and I'm saying, you're like, let me do it again. Anyways, so anyways, that's 9 volts. Now imagine 120 volts. Yeah, that's why if you guys start messing around with electricity at home on the walls or light fixtures, be careful because that can kill you. Okay, it's 120 volts. Especially, I don't know, back then, some light bulbs, sometimes when you got them out, they broke and some part of it stayed in, and some of you try to get that out with your hand. That's very dangerous. What's that? Oh, yeah. So, yeah, be careful. However, that's at home and at stores and anything that comes from the ground, right? But in cars work on a battery. Same thing with the electric cars that we have out here that they're driving around, Mr. Cruz and all them. They work on small batteries. Those batteries start at 12 volts and they go up to 24 volt or up to 36, depending on the mobile device. Some tractors have about 4 different of those batteries and it goes up to 90 some volts or whatever the case, or I'm sorry, 48 volts by combining those batteries. But that's what we call direct current. And that's why in cars, one of them is red, one of them is black, because you cannot alternate those. That's directly that to that. Okay. So the current is measured by impedance. What is that? The amount of current that is flowing through a circuit. It's known as what? Impedance. The amount of current flowing through a circuit is known as what? Impedance. And the symbol that we use to measure is known as an ohm, or the Greek letter O. Here's a Greek letter O, known as ohm. So check this out. So yesterday we started with this table, is that correct? Today we're gonna add numbers to this. Don't copy this, but pay attention. Whenever I talk about a resistor and I give you the ohms, let's say whatever the number of ohms, that translates only to a real number. When I give you an inductor with certain ohms, that translates to an imaginary and it has to be a positive. And a capacitor, also in ohms, it's going to translate to an imaginary, but it's going to be a negative. Let me repeat that again. The resistor is just a number. An inductor is an imaginary, which is positive, and a capacitor is an imaginary, but it's a negative. So on your Cornell notes, copy this diagram, write example Q, copy this diagram, not the table, the diagram here. It shows you an input of 120 volts, and it's got 4 ohms up here, 3 ohms here, and 5 ohms there. And copy this table down here, and I'll give you some time to do that. Ready to go. All right, so you should have copied the diagram. You copied the table. So let's get started. Here we go. So we're going to go ahead and label first our diagram with our initials, yes? So let's see. What would I label this component right here? R for resistor, yes. How about this one? I, okay. And of course, the last one is C. Did everybody see what we're doing? Yes? Okay. Now check this out. Here he goes. I'm going to start with a resistor. What is the impedance, or the amount of current that can pass through that? Here's a resistor. It's 4 ohm. Okay. So how would I write it here? Well, it says here that I just use a what? A real number. So what would this translate into? 4. That is correct. Just a number 4, because it's a real number. Next, let's go to the inductor. What is the impedance on the inductor? 3 ohm. Okay. However, how does that translate into numbers? It's an imaginary and it's a positive. That's why it's greater than 0. So this would be what? 3I. 3I. All right, let's go to the capacitor. The capacitor is how many ohms? 5 ohms. And how does that translate into numbers? It says it's an imaginary, but it's less than 0, which means it's a what? Negative. So it's negative 5I. So make sure we got it, bless you. A capacitor is going to translate into a negative imaginary, and the inductor is always a positive imaginary, and a resistor is always a what? A real number. Whatever number they give you, that's the number. Okay? From 1 to 5, how many are you translating into that? Yes. Okay. All right, let's do another one. So we got this. There it is. There it is. There it is. Look at this one. Don't copy it. Just look at it. Center yourself to see where you're at. Lock your toolbar. And I want you to write on the table the impedance for that. Copy and go. All right, let's see where we're at. All right, look up to your screen. This is the correct answer on your screen. Hands if you got something like that. Yeah, 9, 7i, and negative 10i. Okay, let's do another one. Fill that one in, lock your toolbar, and write the impedance for those. Hurry up, hurry up, hurry up. Should be almost done. All right. Correct answer on my screen. Check it out. Hands if you got something like that. Okay, good. And one more. Crank it up a notch. Let's see how you do with that one. Give you some time. Copy that and go. Here's the correct answer on my screen. Talk it over, you never let them know how they got that, please. How did they get that? All right, how do we get that, Miguel? Very good. Miguel said by combining like stuff. So 4 ohm on the resistor plus 5 ohm on the resistor gives us 9. Then we got 2 capacitors right here, -2, 2 ohm, 3 ohm become 5 ohm, and it's a negative. And this one is 7. Okay, we got this, yes? From 1 to 5, I'll come to bar you with that. Okay, because right now I'm going to add one more column to this table. All right, here we go. So before I add the column, copy this formula that's on your screen. The voltage formula is V equals I times Z. V equals I times Z. I is how much current is being delivered, and the Z stands for the impedance or resistance of each of the components, how much current can go through that, okay? I'm gonna leave that up here, and I'm gonna forward your screen so you can copy example number 6 on your paper. Copy the diagram and copy that table. Copy the diagram and copy the table. I'll give you some time for that. Hurry up, please. Copy and go. All right. So, according to what we have in front of us, let me make some space here. It says here that they want us to figure out the voltage going through each component, okay? However, we already know how to write the impedance for each piece. Is that correct? So let's see. First, I'm going to label my diagram so I know what I'm looking at. So this I would label R. This I would label I. And this I would, oh, sorry. And this I would label C. Does everybody see what I'm doing? Yes. Okay. So let me start with my resistor. Resistor, what is the impedance? 4 ohms. So I would write what? 4. Okay. Inductor, it's 3 ohms. So I would write what? 3i. Capacitor is 5 ohms. So I would write -5i. Okay. Now, for those of you that are a little bit still confused, draw an arrow, a green arrow, and label that to the Z, because that's what we're going to substitute into the formula. And in red, this is our current that we're going to substitute in for the letter I in our formula. So I'm going to start with the resistor. Let's do the resistor together. So I'm going to figure out the voltage just for the resistor, and I'm going to use the formula V equals I times Z. So to figure out the voltage, I need the current. What is the current? 24 plus 12I. Will that always be the current? No, the book's probably going to give you different currents. I'm just giving you an example. So the current is 24 plus 12I. And we're going to multiply that times the impedance. What is the impedance of the resistor? 4. So that means I'm going to distribute that in here and in here. And that gives me, let's see, 4 times 24, that's 96. And 4 times 12I, that's 48I. And this is the voltage going through the resistor. You're like, that's straightforward. Yeah. Let's do the inductor now. For the inductor, I need the voltage. I need the current. Still, the current is the same, 24 plus 12I. But now what is the impedance for the inductor? 3I. I'm going to distribute that 3I in here. 3I times 24, that's 72I. 3I times 12I, that's positive 36I squared. Am I done? No, we need not forget what? The -1 for the I squared. So what is -1 times 36? -36, and at the end we write positive 72I. Hold on, before you go, finish up the last one. Finish up the last one. And take a quick poll at the end, see how you did. Once you're finished, go ahead and log out. And once again, your home place page is 135, 136. Enjoy your home play, guys. See you guys tomorrow. Bye.